It is the most bizarre theory ever proposed in the history of science. Einstein couldn't get his head around it. Electrons can vanish, reappear someplace else. Electrons can be two places at the same time. And exist in multiple states at the same time. Now, that's stupid. I mean, how can you possibly exist two places at the same time? How can you be in multiple states simultaneously? This is insane. This is absolutely counterintuitive. But the problem is, it's right. That's how our world is constructed. Our world is stranger than you realize at the atomic level.
Welcome to the universe in a seashell, the podcast dedicated to science, life, and girl power. I'm Kara Bartek and I'm your host. I'm a PhD, an author, and I want to make this world a more equal and opportune place, one girl at a time. Welcome to the universe in a seashell. Is that a good spooky voice?
I don't know.
Welcome to the universe in a seashell. Is that kind of like a witch voice?
No.
Well, I'm feeling really spooky because Halloween is just right around the corner, and we've been having so much fun covering spooky topics during our bug series. But for our special Halloween episode, I wanted to put the insects on hold just for a moment so we could cover some of the more spooky, mind-bending, rule-breaking, and kind of creepy aspects about science. What do you think?
I'm in for it.
Okay. You in for the long ride then?
Yep.
Okay, so I wanted to remind everybody who's out there listening, if you're digging this podcast, if you're enjoying what we're talking about, if you're laughing on your way to school, if you're giggling at all of our fart jokes, or if you're actually learning something, maybe about bugs, maybe about dinosaurs, or maybe about spooky science, please make sure that you hit that notification button or subscription button, depending on what pod player you're listening in. It would also be really great if you could give us a rating and review, because that raises the visibility of the podcast. And the universe in a seashell is all about making this world a more equal and opportune place, one girl at a time. Right, Cece?
Yep.
Okay, so I want to give a huge shout out to one of my friends, Sheena. What's up, Sheena? I know you're listening in your minivan on the way to school. I hope you guys are staying warm and dry there in Corpus Christi, Texas, because the weather's kind of getting really terrible around here, isn't it?
It really is.
But we're bundled up. We're actually not shooting the podcast from the back porch, which is a little disappointing because you can't hear all of the crickets and cicadas and coyotes, but we're snuggled up on the bed.
Yep. We're basically shooting a podcast on a bed.
Cece's got in her emoji jammies, and she's got one of her marshmallows.
Squishamallows.
Okay, so this is a new thing for me. What is the significance of a squishamallow?
They're softer than a marshmallow.
But they also double as a pillow?
Yes. They're basically a stuffed animal / pillow.
It's a pretty good combination. Okay, so this episode, what we're going to be talking about are some of the spookiest concepts in all of science. Now, did you know that science can be spooky?
No.
Okay, because, right, science is usually all about rules. It's kind of like things need to be one way and they can't be the other. But there are parts of science that really defy the rules. In fact, they kind of move to the level of being a little creepy. Okay, so I want to drop 10 science facts on you that may give you the heebie-jeebies just in time for Halloween. Man, my scary voices are way off.
Yeah.
Okay, I tried. Okay, so the very first spooky fact that I want to tell you guys about is all about atoms. Now, atoms are the smallest building block out there, right?
They are so small.
They make up everything. Don't they?
They make up our air.
They make up your squishamallow.
Yeah.
They make up our Halloween candy. They make up everything.
They make up the computer that we're working on right now.
Absolutely. But did you know that atoms are actually, and I'm going to read this. This is actually the scientific number. 99.9999999% empty space. That is, let's see how many nines that is. 3, 6, 7. That's 7 nines, okay? 99.79 empty space, okay? So let's think about that for a moment. That means basically everything is empty space. If we're made up of atoms and they're that much comprised of empty space, then kind of everything's empty space, okay? Mm-hmm. Atoms are not stagnant particles. They're actually filled with energy and surrounded by electrons that are kind of buzzing around, okay?
Like you see that logo that looks like an atom sometimes?
Yes! And that
and
kind
it
of
has those rings around it?
Yeah, and so those rings kind of represent the motion, and that's what they're doing. Now, a lot of people have described the look of an atom as kind of a cloud, okay? So you can't actually see it staying in one place. Now, no two electrons can actually exist in the same place at the same time. This ultimately means that if you wanted to try and walk through a wall, which again is mostly empty space, your electrons and the wall's electrons would have to exist in the same space, which basically makes it impossible, okay? So while we are 99.9999999% empty space, even if we want to walk through a so-called solid object, we can't. Because the main force that keeps us away is what?
Atoms?
Those little electrons kind of repelling one another.
It's like a magnet.
Yes. Okay, now I pulled something great during my research. The best way to visualize this is to picture a fan. Okay, now as the blades spin rapidly, the internal quote-unquote empty space of the fan does not change in volume but in position, okay? So that means it's not getting bigger or larger. It just changes where it's at. So, if a fan is turned off, you can see very clearly the blades, right?
Like we have a fan above us and you can look at it and see the blades and how many blades there are, how long they are.
Now, what if we turn that fan on really fast?
You would not be able to see anything that's happening.
Absolutely. Now, that's what's happening with these electrons, okay? So again, that's kind of why we describe those atoms as being, clouds. But the way that they are, quote unquote, making up space and giving us the illusion that they're solid is the fact that they're moving all the time, okay? But again, in reality, our universe is 99.9999999% empty space. It's kind of weird, kind of spooky, okay?
That's a lot of nines.
Number 2 on our list is, since the fact that electrons repel, one another, right? That's what we talked about with the atomic cloud and the way that we are living in the universe that's mainly empty space.
Like if I try to put my head through my squishmallow, I am not able to.
Right. So since electrons are actually repelling one another, we never actually touch anything, okay? So let's think about this. This is kind of a spooky fact. The way that atoms are created, the way that the electrons move around, because they are constantly repelling one another, we never actually touch anything.
Like come in contact with it?
Right. Okay? So, this is a basic fact of physics. What we call touching is actually our brain interpreting the electromagnetic force between atoms created by this, what they call electronic repulsion, or basically the electrons not wanting to touch one another, okay? So, we're not technically touching anything. It's just our brain kind of saying, hey, this is what's happening. So in a way, our brain's kind of tricking us. It's kind of weird.
Our brain is like a witch tricking us.
Kind of spooky. Okay? So, it's kind of a creepy fact, right? Now, our third fact on the list is the fact that 85% of the universe is made up of something that we totally don't understand. Now, you would think, look, this is a podcast all about science, right? Science is about understanding. It's about discovery. It's about creating new theories. We should know almost everything about the universe, right?
But we still don't know everything.
Okay, so I want to introduce you to a kind of creepy, spooky, really out there concept called dark matter. Okay? Now, dark matter is a bunch of particles that exist out in space, but they do not absorb, reflect, or emit light.
So it's basically kind of like a black hole?
It's a little bit different than a black hole because black holes actually emit radiation. We can detect them. It moves the mass around it. But dark matter really has no way for us to detect it through electromagnetic radiation, that's the main way we see things out in space, is they radiate, they give off light, they emit some sort of energy that we can pick up on all of our instruments, our telescopes, our sensors, stuff like that.
But the thing that's the same between black holes and dark matter is that they both don't take in light.
So black holes do take in light. In fact, they compress it. Dark matter. Okay, so
I'm thinking they don't let out light.
Yeah, they don't let out light. And this is really good. I'm glad that you're asking these questions. So a black hole is technically just a super huge star that has collapsed in on itself. Now, dark matter is something that fills the universe. And like I said, it doesn't absorb, reflect, or emit light. So it's a material that technically cannot be seen directly, but we know that it's there, okay? We know that it exists because it has an effect on objects around it, and we can observe that effect. So again, we can't observe dark matter directly, but it affects the things that are around it.
Just like a black hole?
Yeah, kind of like a black hole, except for the fact that we can see black holes.
Yeah.
Dark matter, we can't see.
Yeah.
Does So it's kind of weird. It's kind of creepy.
You just have to look around to see if you can find anything to just find it.
Right, but here's the strange thing. People, specifically scientists, they don't really know what dark matter is. There's a lot of hypotheses about it. Some people think that dark matter might actually be a whole bunch of different things that we can't quite figure out. Some people think it might be one thing, specifically subatomic particles. And so when we're talking about subatomic particles, I mean the things that are even smaller than atoms. But again, we don't know. And hey, 85% of our universe is made up of this. Kind of spooky.
That's a lot.
It's a lot.
Like a lot.
Okay, number 4 on our list is the fact that time is an illusion. What do you think about that?
Time is an illusion.
Time doesn't really exist. Okay, now listen. Okay, Albert Einstein, which we know him, right? He's got this super wicked, crazy hair. He discovered so many important principles in physics. He showed that time is it is an illusion through the concept of general relativity, okay? Now, what he says is that time is relative and it varies for different observers depending on how fast you're going, okay? Einstein, he called time the 4th dimension. So he didn't really think of time as something being on our watch. He thought of it as being part of our universe, kind of like space is a dimension.
Yeah.
Okay? He thinks that time is also a dimension. Now, we know his very famous equation, right? E equals mc squared? You've never seen that?
Yeah.
Okay. Yeah, so that's super famous. And what that means is energy equals mass times the speed of light squared. Okay? Now, what that represents is the theory of relativity, or general relativity, a lot of times that it's called. And so again, this is going back to the idea that time is relative. Okay? Now, a lot of people are very confused by what general relativity is. And it is. It's very, very confusing. So I'm just going to give you a very brief overview. Basically, it's kind of the theory of gravity. The idea is that instead of being an invisible force, gravity, that attracts objects to one another, gravity is actually curving and warping space. Okay? So, in another way to think of it, depending on, okay, so let's say there's a huge star out there, okay? A really big one. Depending on its size, its weight, its mass, space actually bends around it, okay? It actually changes how space is shaped, which is kind of a crazy, if you can imagine somebody holding a sheet really tight, okay? Like you've got one person holding one end and the other person holding the other end. And you put like something like a bowling ball, something super heavy and round. What would happen to that sheet that's being pulled really tight? Would the sheet kind of curve down? Mm-hmm. Yeah, it would create kind of like a little depression, right? Depending on how heavy it was. Now, if we just put a marble in there, what would it do?
It wouldn't really move anything.
Yeah. So that's what Einstein said. He says that space curves and bends depending on mass, okay? And the same thing goes for time. But time is really connected to speed, okay? Now, a very important physicist, Carlo Rovelli, said that time is an illusion. Here's what he said. It's our perception that it flows corresponding to our reality, okay? He says what's happening is that there's just a bunch of things that happen in our life. And once again, it's our brain just interpreting how these things happen.
It's our brain being a witch again.
There you go, okay? So again, kind of a spooky concept. Kind of eerie. It's kind of disconcerting to think that time doesn't really exist, right?
Why do we even have clocks if it doesn't exist?
Because we still have bedtimes.
I wish I didn't.
You don't want a bedtime?
No. No.
Okay. Now, number 5 on our list. Time stops in black holes. Okay, so this is one of the things that you were just talking about, black holes. So we've already said time is an illusion, but we don't really think of time as being something that can start and stop, right?
Yeah, time just happens to us.
Well, let me tell you what happens in black holes. To a distant observer, clocks near a black hole would appear to tick more slowly than those further away from the black hole. Due to this effect, known as gravitational time dilation, an object falling into a black hole appears to slow as it approaches the event horizon, or that space around the black hole, taking an infinite time to reach it. So, translation, basically, the closer you get to a black hole, the slower time gets. Because again, we talked about, this goes back to Einstein's theory of general relativity.
So,
as things are big and heavy, it changes the way space is around it. It changes time.
So if like an astronaut went near a black hole and they had a clock in the shuttle or something,
Yeah.
the time would start to slow down.
Yeah, it would tick much more slowly. Now, it would be to the people who are back on Earth watching it. Okay? Their time is going to continue to go
At the same
same.
speed.
Right. So that's see, and this is the creepy, mind-bending, crazy part about science. It seems like those two things shouldn't be able to exist together, right?
Yeah, they should not.
Okay. Number 6 on our list. Time stops at the speed of light.
That's weird.
Okay, just like time slows down when an object moves at a high speed, the same object will also get shorter in its direction of motion. At the speed of light, time stops and the object will shrink to 0 length. Okay? Kind of weird. So if we wanted to travel to like a really far away galaxy, and we travel faster and faster and faster, approaching the speed of light, which is, for us, the fastest anything can go, right? We can go 70 miles an hour on a highway, but the speed of light is way faster than that. Our clocks would slow down relative to an observer back on Earth, just like they do with black holes. And yet, we still would be reaching that distant place out there in space much quicker, okay? It's kind of weird. This is that whole idea of gravitational time dilation. This is where things get super spooky. Time should exist the same way it exists on Earth, but that's not what really happens. Kind of weird, right?
Mm-hmm.
All right. Now, number 7 on our list. Observation affects reality. Okay, so let me translate this for you guys. That means what my beliefs are actually change the way that atoms behave. It can change physical matter. Now, do you believe that? That kind of sounds like magic, doesn't it?
Mm-hmm. It really does.
Okay, so this is one of the crazier principles in quantum theory. And this is, when I say quantum theory, I'm talking about the super, super small understanding of our universe. The deal is that light can exist in both waves and just regular old particles, okay? Shoot out like a beam. Now, depending on who's watching and what they believe that they're observing, light will react to that, okay? So do you see what I'm saying? Light can be a wave, it can be a particle, but depending on who's watching it, that's how it will behave. Now, does that make any sense to you?
No.
Science should say, hey, this is, light is a wave, light is a particle, and it's one or the other, right? And it shouldn't have anything to do with the person that's watching it, but that's exactly what happens. Okay, so there was this very famous experiment called the double slit experiment. And this happened back in, let me see, 1801, and it was by Thomas Young. Now, so the long and short of it is that he created an experiment where he was passing light through these little slits, and on the back end he would be able to understand if light was coming through as a wave or if it was coming through as a particle, because that's what he wanted to understand. He wanted to say once and for all, light is either a wave or it's just a regular old particle. Well, what happened is that he was recording a change or a difference between it coming in as a wave or coming in as a particle, depending on who the observer was. Okay? That's kind of weird, right?
Mm-hmm. So, like, if let's just pretend, if I watched it, it would be a wave. And if you watched it, it would be a particle?
It depends on what you think light is. Do you think light is a wave or a particle?
I think it's kind of a particle.
You think it's a particle? Mm-hmm. Well, then it would probably come in as a particle for you. Okay.
That's cool.
All right, so that's number 7. Now, number 8 on our list is the idea of superposition. Okay, so we already talked about during number 7 that really the state of light can depend on who's looking at it, who's watching it. Well, let's talk about superposition. Now, I'm going to say this, and this is going to sound really scientific, but we'll decipher it, okay? The ability of a quantum system to be in multiple states at the same time until it is measured, okay? So translation. This goes back to that principle that we were just talking about in the double slit. It can be 2 things at once until somebody looks at it. So light is technically both a wave and a particle until somebody measures it or observes it. Now, how does that happen?
I don't know.
Okay, so I'm going to tell you a little story about Schrodinger's cat. Now, this is not necessarily superposition, but this is what scientists call a thought experiment that will help you better understand this idea. Okay, so Schrodinger, now this didn't really happen, okay? Schrodinger just wanted people to think about it. Okay, so he put a cat in a box. Now remember, this is all just him making it up. No cat was harmed in Schrodinger's experiment. Now, so what he did is he theorized or hypothesized that there would be a cat put in a box and there would be poison in there. Okay? Now, this poison would either open up and kill the cat or it would stay closed, depending upon some random variable. Now, the box was totally sealed, and nobody knew if the poison was going to open up and kill the cat, or if it was going to stay closed up and the cat would live, okay? So what Schrodinger said, the cat in the box, since we don't know what's happening, is both alive and dead at the same time.
That makes no sense.
Thank you. See, here we get into the creepiness. So what he says is there's 2 realities that exist. In one reality, the poison opens and it kills the cat. Okay? And in the second reality, the poison doesn't open. It keeps on meowing. Meow, 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 meow. Wants some milk, eating some Friskies, pooping in a box. Okay? But... oh, you like that pooping in a box? That perked you up a little bit. And he said that until you open the box, those 2 realities exist. But once you open the box and we know what's happened to the cat, the reality wave collapses. Okay, so that's kind of like how superposition works. Light is both a wave and a particle, okay, until somebody observes it. So again, this is a rule-breaking principle of science. But guess what? This exists, and this is something that scientists work through every day.
I'm still laughing about what you said about the cats.
Listen, no cats were harmed in Schrodinger's experiment. Now, I don't know about if the cat pooped or not, but okay. Number 9 on our list is the principle of quantum entanglement. Now, this is one of my favorite principles. So, quantum entanglement states that once two particles have been in the same system and they are, for whatever reason, taken apart, they continue to act as if they are still together.
I know this one.
Yeah. So, for example, so we generally observe quantum entanglement again at that atomic, subatomic level. So we're talking about electrons. So if two electrons are together and they're getting in the spin cycle, spin up, spin down, spin up, and we take them apart, even if we separate them by 1 billion light years, they will continue to act as if they have never been apart.
If we put one in Europe and one in South America, they'll still be together.
Yeah. So, I mean, and so what does this tell you about the nature of reality?
Right, reality is weird.
Reality is weird, okay? So it kind of makes you say, well, maybe space itself is an illusion. Because, you know, we're already talked about, we're basically living in a universe that we don't understand.
I think my world is an illusion.
Oh, look at you. Do, 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 do. Twilight Zone, okay? Now, our very last principle, and this is appropriate, number 10 on the list, is the principle of uncertainty. Okay, sometimes this is called the Heisenberg uncertainty principle, named after a German physicist named Werner Heisenberg. Werner Heisenberg, okay?
Werner Heisenberg?
Yeah, he talked about this in 1927. Now, he says that things can never technically be measured. Okay? So listen to this, okay? Now it's easy to measure both the position and velocity of like cars, okay? Because, you know, we're in a car, we know exactly how fast it's going and where we're at. Now, but here's the deal. They're saying things that are very, very small, atoms, electrons, all of that kind of stuff cannot actually ever be truly measured, okay? He's saying that there is uncertainty in position and velocity because things are so tiny. The very concept of exact position and exact velocity have truly no meaning. Okay? So, and you know what? This summarizes everything on our spooky list. We basically said that the majority of space is made up of something that we don't understand. Atoms are basically empty space, which means that we're technically living in a very, very empty world. And we don't actually ever touch anything, right?
I touch plenty of stuff during the day.
Okay. Science says otherwise.
I know.
Now, I don't even have to ask you what your favorite part of this list was. It was the cat pooping, wasn't it? All right, guys. Continue to tune in for more fun, crazy, and exciting things on the Universe in a Seashell. Drop me a line. Let me know if you're enjoying this, what kind of topics you want to cover. More importantly, make sure you're hitting that subscription notification button and leave us a rating and review. Thank you for listening.
Bye.